Couple of special graphs now, not special in the sense that there's anything particularly weird going on, just in that they're quite useful ones to be able to draw without having to do much working out. And the first one that we're going to have a go at is this one, y equals x. Nice classic graph. For any input and output pair for this graph, y equals x, there will be something that's true about them. If y equals x, then whatever x we input, the output y will be exactly the same. So if the input is 0, if x is 0, then y equals x and y is 0. So there is a point on my line. X is 0, y is 0, 0, 0. If x is 1, then y is the same. 1, 1, 2, 2, 3, 3, 4, 4, and so on. And also minus 1, minus 1, minus 2, minus 2, minus 3, minus 3, minus 4, minus 4, and so on. We're getting a nice straight line which we can then join up. And there is the line y equals x, where input and output x and y are the same. So we get pairs of coordinates 0, 0, 1, 1, 2, 2, and so on. Pairs of coordinates where the x number and the y number are exactly the same. Second key example that we're going to have a look at is this one, y equals minus x. Very similar equation, but with a minus sign this time. We could think about that in terms of coordinates first. Sometimes thinking about the coordinates is quite helpful. If, for example, we have our coordinates, our x number and our y number, if our x number is 1, then our y number is going to be minus that, so minus 1. If our x is 2, then our y is going to be minus that, so minus 2. If our x number is 3, then our y number is going to be minus that, so minus 3, and so on. We could start plotting those. So 1 minus 1 is there, 2 minus 2 is there, 3 minus 3 is there. 3 points, that's plenty to be drawing a line from. We could do more if we wanted to check. I suppose we could fill in 4 minus 4, say, and it seems to be following this nice pattern here. And we're going to end up drawing in, when we draw in the full line and extend it beyond just those points that we've worked out, we're going to end up with this line here. I think we should do, we should probably label it y equals minus x. A couple more special cases we need to be aware of, and that's things like this. So again, draw the graphs of. We're going to draw y equals 4 and y equals minus 2. Bit weird looking this time. We don't have a formula so much as just y equals a number. Well, how can we possibly draw a graph of that? Surely that's just a statement, y equals 4. Well, yes it is, but we can still draw it as a graph. Think about the coordinates. All coordinates are made up of two numbers, an x number and a y number. In this particular one, y is not dependent on x. The output y is not based on what input you put in, what choice of x you make. This time, the output y is 4. That means we are plotting all of the coordinates where the second number, the y number, is 4 for any input value at all. When the input x is 0, the output y is 4. When the input x is 1, the output y is 4. When the input x is 2, the output y is 4. When the input x is 3, the output y is 4, and so on for any value of x. We're getting clearly a nice straight line, this time a horizontal line across the grid, crossing at 4 on the y-axis. So y equals 4. Crosses the y-axis at 4. For this second one, we can make a prediction what that will look like. Horizontal line crossing the y-axis at minus 2. So this. Crossing the y-axis at minus 2. Final pair of special lines that we're going to have a look at, these two examples. Draw the graph of x equals 3 this time. So previously we've just seen two graphs with y equals numbers. These to our x equals numbers. You can probably see where this is going, but let's make sure we know why. So any coordinate is a pair of values, an x and a y. This time we are forcing the x number in the coordinate to be 3. So we are looking at every single coordinate where the x value is 3. For example, 3, 1, 3, 2, 3, 3, 3, 4, 3, 5, and so on. 3, 0, 3, minus 1. All of those, they are each coordinates. They are all coordinates where the x value is 3. We are forcing that first value to be 3. We are clearly getting a nice vertical line this time, cutting through the x-axis. So x equals 3 cuts through the x-axis at 3. Probably make a prediction about where this second one's going then. So we're going to draw the line x equals minus 4. It's going to be a vertical line because it's an x equals number, y equals a horizontal, x equals our vertical. Where's it going to cross? Well, it's going to cut through the x-axis and it's going to cut across at minus 4. So it's going to go here. If you were asked to draw these in a question, probably going to be a 1-mark question, but it is entirely possible you could be asked to do something with them that we will come back to in a later lesson. Just to really hammer that point home, lines with the equation y equals a particular number are horizontal. That's left to right, and they cut the y-axis. And lines with the equation x equals a particular number are vertical, that's up and down, and they cut the x-axis. There are practical uses to graphs as well. All of the graphs we've seen so far have just been generic rules connecting an input x and an output y to particular quantities, not having any particular meaning or context on them, just an input x and an output y connected by some rule. Now we can also draw graphs that connect to actual physical things. It could be, for example, a graph showing the link, the relationship between two different units of measurement, like in this example here. It could be how to switch between the number of hours that somebody's worked and the pay that they get for that work. It could be the link between two different currencies. This graph here is showing the link between inches and centimetres. You can use this graph to change between inches and centimetres. And then there is a line. That line is generated from the connections, the links between different inches and centimetre values that line up. And they've been joined into a straight line. And we can use this graph to convert between the two measures. Part A, change 3 inches to centimetres. Now we have done this kind of thing before. This is exactly the same as the, if you know the input, work out what the output y is, or if you know the output y, work out what the input x must have been. It's exactly the same thing, just that we're switching between two particular units here. So if we wanted to change 3 inches to centimetres, I'm going to have a look at my axes, the scales on my axes, and see if I can read the 3 inches off there directly. Well, yes, I can. So on the bottom we've got 0, 2, 4, 6, 8 and 10 inches. Presumably then 3 inches is going to be here somewhere. What that means is that I could look up from the 3 inches to my graph. I'm going to draw in the line to show that I know what I'm doing. There it is. So I've drawn from the 3 inches up to the line of the graph. Once I've done that, I'm then going to draw across to the centimetre scale on the other side. So we have inches along the bottom and centimetres up the side this time, rather than just generic x's and y's. By drawing in both lines, I've shown that I know what I am doing. Now I need to work out where that is. So on the centimetres we have 0, 4, 8, 12, 16, 20, 24 and 30. That means that somewhere in here is a number between 4 and 8 that this comes out as. that will be a sensible thing to give as an answer. The halfway point between the two must be 6. There are then 1, 2, 3, 4, 5 squares that cover that 2 jump from 6 to 8, which means each one must be 2 divided by 5 is 0.4. So 6.4, 6.8, 7.2, 7.6 centimetres. And that's going to be my answer for that first part. Second part of the question then. Change 50 centimetres to inches, so the other way this time. So we're starting on the vertical scale. So I'm going to look at my vertical scale, I'm going to find the 50 centimetres and, oh, I'm going to hit a problem. Because that scale does not go up to 50. The largest number on the scale is 30, but actually it stops somewhere before that anyway. It stops just after 24. So we've got a little bit of a problem. We can't directly read 50 centimetres off the graph. So we're going to have to think cleverly. We're going to have to choose something else to read off there. So I'm going to choose to read 10 centimetres off the graph. I'm going to choose to switch 10 centimetres into inches. So I'm going to go across from the 10 to my graph line. There we go. I'm then going to draw down to the inches side. And again, it's a good idea to actually draw these lines in so that you are showing you know what you're doing, just in case your final estimate is slightly off. Depends on the scale of the graph. If you've drawn things in, then you're showing you are trying to do the right thing, even if your estimation is slightly out. This comes out as a nice, easy to read 4 inches. So we've got the fact that 10 centimetres is equal to 4 inches. Well, so what? We weren't interested in 10 centimetres. We were interested in 50 centimetres. So how could we use the 10 to get to 50? Well, if 10 centimetres is 4 inches, we could have 5 lots of that 10 centimetres, which means we'd have 5 lots of the 4 inches. So we'd have 4, 8, 12, 16, 20 inches. We've already seen that any formula or equation looking like that, with any value for m and any value for c, where again remember they are just placeholders, anything that looks like that, some number of x's plus or minus a particular value, we've already seen how they generate straight line graphs. Sloping either upwards or downwards from what we'd expect, but straight lines nonetheless. Now different equations, different rules will generate different looking graphs. Change this, we change the graph. Different numbers gives us different straight lines. Choosing an equation that's completely different to this, however, will generate a different shape of graph. Really though, that shouldn't matter too much, because as long as we can use the rule to work out some coordinates that would work, plotting those coordinates will probably give us enough of a shape. Now, generally speaking, you will be asked to draw straight line graphs, but it is possible you could be asked to draw a different kind of graph or look at a different kind of graph. And they are graphs associated with quadratics, which, as a reminder, is any equation that's got one of these in it, an x squared term. So it could be something as simple as y equals x squared. Or it could be something a bit more complicated like this, y equals 3x squared. Or it could be something even more complicated, something like that. As long as you can set up a table of values, find some matching input x and output y values, turn them into coordinates, plot them on a grid, look at the shape that's being made, and handily, quadratics do all have a standard shape that we're expecting. We'll find out what that is as we go. As long as you can plot the coordinates and recognise that the standard shape is being made, then we can draw the graph. Like this one, for example. Draw the graph of y equals x squared for x between -4 and 4. And then there's a table of values, and then there is a blank coordinates grid for us to fill the points in on. So let's see if we can work out the table of values. We might have to do a bit of substituting this time. The rules from before about jumps and things don't strictly work with quadratics. They only tend to work with the straight line graphs. So we're going to have to actually just work out some points. Let's ignore the negatives for now. Let's focus on the positive numbers first, because they're generally going to be easier. This isn't a bad one to substitute into though. So what we're going to do is we're going to substitute each of these values in one at a time, the different values of x, the different inputs, and we're going to work out the output in each case. So when x is 0, when our input is 0, our equation, it squares it and gives us an output. So 0 squared, 0 times itself, 0 times 0 is 0. So there's one of our points, 0, 0. The next one, 1 squared, 1 times 1 is 1. 2 squared, 2 times 2 is 4. 3 squared, 3 times 3 is 9. And 4 squared, 4 times 4 is 16. So we filled in half of the grid. Notice again that there is no particular jump going on. There's a jump of 1 and then a jump of 3 and 5 and 7. We're not going to see patterns of quite the same nature in this case. But we could work out the negatives here. Now we have to be careful with this because we've got to think about those signs going on. If we're thinking about -1, for example, we'll be doing -1 and we'll be timesing it by itself. Well, -1 times -1. 1 times 1, if we ignore the signs, is 1. So our answer is something to do with 1. But is it +1 or is it -1? Well, we've got 2 minuses. We'd be expecting to be a positive number. 2 minuses though. 2 changes of direction. 1, 2. We're back on the positive side and it's going to be a +1. -2 times -2. 2 times 2 is 4, so the answer is something to do with 4. Is it +4 or is it -4? 2 minuses, 2 changes of direction again, so it's going to be a +4. We're going to get the same thing for the -3, so that'll give us a 9, and we're going to get the same thing for the -4, so that will give us a 16. There is a pattern, you'll notice, hopefully, starting at the 0 and working outwards. 1, 4, 9 and 16. The thing about quadratic graphs is they will always repeat. They may not necessarily repeat from 0, they may not necessarily repeat from the middle of this table, but they will repeat on either side. They will be symmetrical from somewhere. And if you can get to the point where you found that value, then you can do a little bit of copying the values up either side. But you have to get there first. We're going to plot those points. I am going to use a pencil for this one because it's going to be important to do the drawing accurately here. So the first coordinate I'm going to plot is this one, 0, 0. I'm going to mark that in there at the middle. 1, 1, 2, 4, 3, 9, and 4, 16. Notice that we are not actually getting a straight line this time. If we were to try and line those up with a ruler, we would struggle. We could join any pair of points, but we're never going to be able to join them all up on a straight line. Which is fine, because we're not expecting a straight line. Let's plot the other ones in. So -1, 1, there. -2, 4. -3, 9. And -4, 16. Hopefully though, now we've plotted those points, we can see a certain shape. And it seems that we've got this kind of U shape. This sort of bowl shape. A nice smooth curve. And that's what we need to draw. We need to draw a nice smooth curve. Do not join the points up with a ruler. We need to draw a nice smooth curve running between each of these. This is why a pencil is useful. It can help to... We're going to freehand it. Might take a couple of goes. A nice smooth curve that runs between each of those points. With the pencil, of course, the beauty is we can just change it if we've missed a little bit. And there we go. There is our graph of y equals x squared. We can still use it in much the same way as any other graph. We can still use it to estimate values. It's just that this time we've got a curve instead of a straight line. Now we're going to draw one more quadratic, and this time draw the graph of y equals x squared plus x minus 2. So a little bit more complicated looking, much more like the kind of quadratics that we were looking at a few lessons ago when we were talking about factorising them, expanding from two brackets and factorising quadratics. This standard kind of look, we've got the squared term at the front, the number term at the end, and an x term in the middle. Now this time we've got our set of values and we've filled the answers in already. Just because we're going to focus on the drawing. To generate those values, we do it in exactly the same way. We'd substitute each of these things in and we're going to get certain values out. Notice that there is still this mirroring pattern, this symmetrical pattern, that we've got the -2s, the 0s, the 4s, and then presumably there's a 10 there, and there would be a 10 here if we went down an input. They're not mirrored around the middle this time, and there is no value between these two that are the same. Presumably there is some number between -1 and 0 that gives us a kind of pivot, almost, for where we're mirroring, but they are the values that we would generate if we went through the calculations, the substituting. We can plot each of those then. So -3, 4, first of all. Let's go for that one. And then -2, 0, so there. And then -1, -2, so there. 0, -2, there. 1, 0. 2, 4. And 3, 10. Notice that we still get this kind of U shape. Yes, okay, there'd be another value down here to kind of completely mirror us, but we're still going to get that U shape, and we're still going to draw in, sketch in the smooth curve. The little bump between the two crosses at -2 there. Nice smooth curve. As carefully as we can, and extending it a little bit, show that it does carry on. And we're going to label it y equals x squared plus x minus 2. Standard shape again, that U shape that we'd expect to get from the quadratic, because it turns out that all quadratics will give us that kind of U shape. It might be quite a tall, thin U, or a sort of wider, fatter U. It could be either, but we will still get that kind of bowl cup U type shape any time. Now before we move on from this equation, there are a couple more things that we might want to notice about it, a couple of things that are interesting and might clear up a few lingering mysteries from a couple of weeks ago. Part B of this question, if part A was draw, then part B says using the graph, solve x squared plus x minus 2 equals 0, and there is a hint given there. Look where the graph gives a y value of 0. So what we've done here is we have swapped out y. This was equal to y, but now it's equal to 0. We've swapped out the y for a 0. So we're looking for where we are at 0 on here. And where is the y value 0? As in, where have we gone nowhere on vertically? At which points have we not gone up or down at all? Well, this one and this one. This is the point -2, 0, i.e. a y value of 0, and this is the point 1, 0, i.e. a y value of 0. So, x is -2, or x is 1, i.e. those 2 points. Worth bearing that in mind. Why? Well, let's have a look at part C. Part C says factorise the equation above and solve it. And then says, what do you notice? Well, we're told to factorise it, so let's factorise it. To factorise, remember, we need to first of all set up our standard answer. two brackets with an x in each. We're just looking at a single x squared, so we can just have an x there and an x there. There will then be a number in this bracket with a particular sign and a number in this bracket with a particular sign. And the trick with the factorising is to find those two numbers. These two numbers link to this original equation in a very particular way. The two numbers have to multiply together, times together to give us the 2, and then add together to give us, add or take in fact, to give us the number in front of the x. There is no number in front of the x, but if we wanted to add one in, we could do, and that number would have to be a 1, which we could write in if we found it more helpful to do so. We need a pair of numbers that times together to give us 2. Well, there's only one pair of numbers that will ever work for that, and that is 1 and 2. It will have to be the numbers 1 and 2. I'm going to put the 2 in there and I'm going to put the 1 in there. We now need to think about the signs. We now need to use those two numbers to reach the number 1. Is there a way to reach the number 1 with those two numbers? Well, of course there is. Plus 2, take away 1. Plus 2, take away 1, will leave us with that plus 1. And in fact, plus 2 times minus 1, 2 times 1 is 2, and the minus 1 will give us the minus on there. So there's our factorised bit done. Now we're also told we had to solve it. To solve a quadratic, it had to be equal to 0. Well, handily, it was. That was equal to 0, which means that the factorised form is also equal to 0. Think back to when we were factorising and solving quadratics. The only way we can have two numbers for this, x plus 2 is a number, and this, x minus 1 is a number. If x is a number, then x plus 2 is a number. If x is a number, then x minus 1 is a number. The only way we can have two numbers that times together to give us 0 is if one of the numbers is 0. So option 1 is that x plus 2 is 0. If that is the case, something plus 2 is 0, the something must be minus 2. Or possibly we had the second case being true, that x minus 1 was equal to 0. Something take away 1 is equal to 0, so the something has to be 1. So that means our two possible answers with the quadratic, we always had two possible answers with the quadratic, and without more context we can't accept or reject either of them. Our two possible answers are x equals minus 2 or x equals 1. So having factorised it, we've ended up with this factorised form. X plus 2 and x minus 1. And then we solved it. And when we solved it, x was equal to minus 2 or 1. And hopefully there's something we notice about those two values. Hopefully we notice that they are exactly the same values as where this graph crossed the x-axis, where the value of y was 0. So to think back, with the quadratics, we said there is a reason why quadratics give two possible values. And without more context, we can't decide which, if any, is the correct one. Two possible values because there are two places on the graph. Because of this mirroring effect, this graph being symmetrical about a certain point, either side of that value, there are two possible values that it could take. This one here and this one here, the two crossing points on the x-axis. The two places where the y value is 0. So, to sum up, different equations give different shapes of graph. Different types of equations give different shapes of graph, but there are certain standard ideas between them. It's helpful then if we can look at the type of graph that something is and recognise the sort of shape that we're expecting. The four that we've seen, or the four that we could probably work out from what we've seen, we've already seen positive straight lines. Any sort of equation that's clearly a straight line, so that's that y equals mx plus c type, some number of x's plus or minus a certain number at the end. If there is a positive number in front of the x, a positive gradient, then we are expecting this kind of shape. Different steepnesses, different crossing points, but that kind of shape. If, however, we've got a negative straight line, something like that y equals minus 3x minus 4 that we saw way back when, we'd be expecting this kind of shape. Still a straight line, still the y equals mx plus c type stuff, but downward sloping. positive quadratics then, that's anything with this x squared term in, but a positive number in front of the x squared. 1x squared, 2x squared, 3x squared, etc. That would give us that nice curved U sort of shape with that symmetrical point around the middle where everything's mirrored either side of it. Negative quadratic, that's any quadratic, an x squared containing equation that has a negative number in front of the x squared. So something like a minus x squared or a minus 2x squared, for example. We haven't seen one of those, but it would actually look like this. Still that kind of U shape, but upside down this time. Now, much as we can just have straight line graphs with x's in them, and quadratic graphs with the x squareds, and we can also have graphs with x cubeds in. You are very, very unlikely, in fact it's never going to happen really, that you're going to be asked to draw a graph with an x cubed in, but you might need to recognize one. So it's helpful to recognize that kind of standard shape. Any graph containing an x cubed is said to be a cubic graph, which sort of makes sense. Again, there are positive and negative versions of this. So positive, a positive number in front of the x cubed, 1x cubed, 2x cubed, 3x cubed, and so on. Anything with one of those x cubes in will look like this, kind of like that sort of curved shape. It could be more distorted than that. This could be higher up or this could be lower down, but something roughly that kind of shape. Negative number in front of the x cubed. In negative number, say minus x cubed, minus 2x cubed, minus 3x cubed, etc., would have this kind of shape. Same kind of shape, but the other way round. Top left to bottom right. Now the final graph that we need to be able to recognise is a weird one. It's called the reciprocal graph, and is the graph of the equation y equals 1 over x, 1 divided by x. So we take each of these values and we take each of the input values and we divide by it. We do 1 divided by that number and we get our output value. And this is why this gets weird. So imagine that the x's get bigger and bigger and bigger. 1 divided by 2 is a half, 1 divided by 3 is a third, 1 divided by 4 is a quarter, 5th, 6th, 7th, 8th, 9th, 10th, 11th, 12th, 13th, 14th, 15th, and so on. As the value of x gets bigger, the output gets smaller, because we get smaller and smaller and smaller fractions. So it will get closer and closer and closer and closer and closer to 0 as the x gets bigger, closer to 0. So as x gets bigger, y gets smaller, closer to 0. But we will never actually reach 0. You can never do 1 divided by any number and get 0. It is impossible to divide something into nothing. So we will never actually get to this axis. We will never touch the axis. It will never reach an output value of 0. Ever. Equally, we can't do 1 divided by 0, so we can never have an input value of 0. We can never input 0 as a number. As this value gets smaller and smaller, we're dividing by smaller and smaller chunks, so the answer will get bigger. So as x gets smaller, then y as an answer would get bigger, because it's the opposite to this. But we can never divide by 0. So it turns out that we never actually touch either this axis or this axis. As this gets bigger, we get closer and closer. As x gets smaller, as we're closer to the 0 here, we're getting bigger and bigger answers. So we'll actually end up getting that kind of shape. Now the same will happen for the negative numbers, just that our answers will be negative as well. Input a negative, then you get a negative output as well. You're dividing by a negative number, you'll get a negative answer. So we're going to have this kind of situation down here, this weird kind of idea, where we will never touch the axes, because you can never get 0 as an answer, and you can never divide by 0 as an answer. I appreciate that that was a really quick explanation as to why this graph is this shape. If you want to just accept that it is, because it's a weird graph and it's recognizable, fine, please do. If you wanted to go and read up on it, well, you could always test out some values for yourself. You could go and read up on it on the internet. I'm sure you could find something somewhere that will explain it in detail. Or you could test out some values for yourself and do a bit of plotting and see that it comes out in this shape. Regardless, we need to be able to recognise the shape of the reciprocal graph y equals 1 over x, and it will always look something like this, never touching either axis.